So are we all set here? Does it look good?
Yes.
Okay.
Looks great here too.
So this, my interest in the history of transatlantic communications came about as a result of the Potomac Valley Radio Club's putting the old naval radio station NSS on the air during Armed Forces Day. And I was asked to do a presentation about NSS, which takes you to a lot of history, and some of that's embedded in this presentation. And then you get kind of carried away, and you'll see where that led. So this is a photograph of the NSS station kind of at the peak of its development, probably about 30 years ago. It was a very large VLF array. The central tower there is 1,200 feet high. It's right on the shore of the Chesapeake Bay on a peninsula that's surrounded by water on 3 sides. But the station was ultimately shut down in part because the Cold War came to an end, so peace broke out, I guess. And the other thing is that there's a much bigger VLF naval station up in Maine, which was very well engineered. It's actually built as 2 stations on a single site, so if one station should fail, they can fail over to the other, or they can run both. So this station became kind of redundant. So anyway, it went away, and if you go there today, it's a public park now, and it's just grass and trees. So every clue of the existence of this station is now gone. And when we operate NSS there, we could not do it this year because of the COVID virus. The Navy disinvited us. This peninsula, by the way, is now part of the Naval Academy grounds, which are in this photograph off to the left, about a mile or so. And the Naval Academy has already started to expand onto this facility. They have quite a nice athletic complex that they've built on the former naval radio station grounds, and I'm sure they'll put a lot more out here later. So we operate NSS now in tents, field-based style, kind of right in the middle of the photograph there is where we operate, but at the far northern edge of that peninsula, just before you get to the water. And it's quite a nice site, but it's extremely exposed to the northerly winds, as we found out one year. Armed Forces Day is in May, and that one year, it seemed like it was January when we were operating there at night with the wind coming off the water. So this is a QSL card we used on the 100th anniversary of NSS. It's very similar to the QSL card that NSS used when the Naval Radio Station got on the air during Armed Forces Day for many years back in the 50s and 60s. So this is focused in particular on the history of the Naval Radio Station. I am not going to read all of this. It'll just take too much time, but I'll just focus on some of the key points, and if the presentation winds up on YouTube, people can look at it in detail. But HF radio kind of all began, transatlantic HF radio kind of all began with Marconi's transatlantic tests starting in 1901. There's a lot of controversy as to whether he actually was heard. I'll mention a little bit about that later. Then, of course, the Navy realized that if they didn't have radio capability on their ships, they would no longer be capable of conducting naval warfare against other advanced navies. So that became a big priority in the Navy. And the Navy kind of became the leading force for radio development all during the pre-World War I period and through the war as well. They built a big station in Arlington. I'll show a photograph of that a little bit later. During the war, when the U.S. got into the war in 1917, the Navy seized essentially every radio station in the United States, and radio became a naval monopoly. And ham radio operators lost their privileges, were required to either seal all of their equipment or get rid of it. And ham radio had a hell of a time getting our operating privileges back after World War I. It was not trivial. The Navy did not want to give that up. And I think everything else that's shown on this presentation from this point forward, I'll cover a little bit later in the presentation. So this kind of all began with James Maxwell, and he was a mathematician. And in 1864, he predicted that electromagnetic waves would exist. And this is a book. You can still buy a copy of this book online. It's great for mathematicians, not so great for everybody else. And when he got to the point where he had proven mathematically that electromagnetic waves, electromagnetic fields existed, you know, he kind of declared that he was done. And there wasn't a whole lot of interest in the practical implementation of electromagnetic fields for communications or any other purpose for some time. Then this fellow came along, another name that's familiar to people familiar with the history of radio, and he made it his mission to prove that Maxwell's electromagnetic waves actually existed. But when asked about the applications, so he took it somewhat further, so he proved that they existed. But when asked about applications, there's a quote at the bottom there, and he said, electromagnetic waves are of no use whatsoever. This was just an experiment that proves that Maxwell was right. So Hertz only went so far also, which is why he's not a famous figure in the history of radio communication. He only carried it to the point of proving the existence. And this is how he did it. And we'll recognize some of this stuff even today. You look at the photograph of his laboratory, Hertz's laboratory, he had a dipole antenna. That was effectively a 6-meter dipole. He didn't really need those balls on the end of the dipole, but that's, you know, they didn't know back then what we know today, so you don't need those on a dipole. And his transmitter was a spark gap. And he used a spark coil to generate the high voltage across the gap, and the spark created electromagnetic waves that were radiated by the dipole. And that was his laboratory. And his receiver was just what we would call an electromagnetic or a magnetic loop antenna, a small diameter loop, and his receiver was a spark gap. So when he transmitted with the spark gap to the balanced dipole, and he put the small diameter loop adjacent to it, the spark would spark across the loop, and that was his receiver. And that was the first radio communications that ever happened, right in this laboratory. And he carried it somewhat further to make it more efficient so that he could communicate across the room instead of really short distances, but he kind of declared success once he got this whole thing working. But then this guy Tesla came along, and his big thing in engineering was alternators. He was really interested in AC power, and they became very interested in developing techniques for transmitting high power over distances. And as a result of doing this, he developed high frequency alternators. By this time, the state of the art of electrical engineering was pretty advanced. Streetcar systems were in use, AC power was in use, motors were available, and alternators were widely used to generate AC power. And the technology was advanced enough that they could produce alternators that operated up in the 10, 20 kilohertz range. So Tesla was responsible himself personally for a lot of that technology. And this is from a museum, and it shows what the poles look like on the high-frequency alternator that Tesla invented. It had 384 magnetic poles. It rotated at a speed of 3,000 RPM and was capable of producing 10 kilowatts of very pure continuous wave RF at 10 kilohertz. But you couldn't make a communication system out of this because no one had yet developed a receiver that was capable of copying a continuous wave signal. So the next generation of transmitters that could actually communicate went back to spark so that a simple receiver could could hear the modulation on the waveform. If anyone's ever tried to listen to a CW signal with an AM detector, that was kind of the state of the art of technology back then. And vacuum tube didn't exist yet. So we're talking about a technology here that was kind of electromechanical. The electron tube didn't come until a little later, as you'll see. So then Marconi comes along, and now here's a businessman. So he takes the advancement of the state of the art of radio technology. The term radio didn't exist yet, so this would be wireless is what they were trying to develop, a term that went kind of obsolete until recent years. And he wanted to make this into a business, and he did. So this, many hands have heard about the 1901 transatlantic experiment. Marconi's objective was to transmit from Cornwall on the southwest coast of England with a 10 kilowatt spark gap transmitter, and to be able to receive this signal. Originally his intent was to receive it on Cape Cod, but he had trouble with the weather there and ultimately wound up launching a kite, and I'll show you a photograph of that kite in just a moment. This photograph appears to be original, but there's obviously something that's been added where it says spark over on the right side there. That's obviously been faked into this photograph, but it's probably an accurate representation as to how the spark signal was generated. Maybe that spark gap was in a different room or something. So this photo was edited, but it gets the point nonetheless. The best estimates are that this transmitter was operating around 500 kilohertz, mostly based on the size of the antenna. And here's the transmitting antenna. They originally had in mind a much bigger antenna, but it fell down in the wind. So Marconi was on his way across the Atlantic, and they had to get up a substitute antenna, so this is what they put up. It was 54 copper wires, 150 feet long, fed against ground, and they were right on the ocean front there. Estimate about 1 kilowatt ERP, somewhere based on the size of the antenna, maybe 850 kilohertz. So they were in what we would call the AM broadcast band today. And here's the receiver. It's the state of the art of receivers in 1901. It was called a coherer for a reason. You could only send one Morse element, and the loose metal filings that were in this vacuum tube, it's a vacuum tube of a different kind. It's a type. It's a tube in a vacuum with a small gap in the middle, and the filings, the little metal filings that were scattered in this vacuum, would cohere to those two electrodes when it detected the presence of a electromagnetic signal. So receiving a signal was a real chore. Every time it cohered, when the transmitter stopped, you had to shake the tube, and then the metal filings would be loose, and then when the signal was again received, the metal filings would cohere. Such was the state of the art at that time, and they used a small mallet after each detection of each Morse element to loosen up the filings. Receiving antenna, it was a kite that was flown from the lighthouse at Signal Hill, Newfoundland. There's quite a nice museum at this location if anybody ever finds themselves in Newfoundland. And here's a kind of a pictorial look at it. So Marconi's idea was to create a business, but he had a little bit of a problem here. And his objective was to take the business away from the transatlantic telegraph cables that by now were a pretty substantial business. And they got a lot of money to transmit messages across the Atlantic through submarine cables. And he was convinced that he could take quite a bit of business away. Well, these transatlantic cable companies had a lot of power to influence governments, because governments got taxes from them. And one of those cable companies threatened to sue Marconi, and he decided, well, he'll just move away from Newfoundland instead of getting involved in the legal battle, because he had more important things to do. So he moved over to Nova Scotia for the rest of his experimental work. And this is the first station he built. Looks very impressive. It's a place called Glace Bay, Nova Scotia, way up north. And the antenna is an inverted cone antenna on 4 200-foot wooden towers. But unfortunately, they discovered when they started trying to communicate with this station that it didn't have enough power to be reliable. You couldn't really establish a successful business with communications that was very unreliable. They were still operating in the VLF band, which is very noisy, especially in the summer, but it's noisy in the winter too. So this site, although any ham would love to build a station right on this oceanfront station, right on this oceanfront site, you might not love it so much in the winter, but it was too small. So they had to move. He had to move again. And then along comes another fellow here who invented the high-power CW transmitter. And what he did, Alexanderson worked for General Electric Company. And he took the work that Tesla performed with that alternator that I showed you earlier, the 10 kilowatt alternator, and he turned it into a 500 kilowatt alternator. So this was lots of dB improvement. And this is what one of the spark transmitters looked like at about the same time. So Alexanderson developed spark transmitters as well as later these very high power alternators. And the synchronous rotary spark that's shown in this photograph was the first successful two-way communication between Cape Cod to the southwest coast of Scotland. Excuse me. It was done at 84 kilohertz, and you can see in the background of the photograph what this synchronous spark looked like. Those are all spark gaps, and the rotary spark gap was driven at a suitable speed to generate the 84 kilohertz. 6 feet in diameter, 50 electrodes driven by a three-phase alternator running at 125 kilohertz. So it was really running fast. So now a new form of communication begins to become invented. Fessenden was the inventor of continuous wave communication and the inventor of the concept of the heterodyne receiver. And I'll mention the superheterodyne in a minute and the difference. But although he invented the superheterodyne receiver, he was never able to build a successful operating receiver because the technologies weren't good enough to develop an oscillator. So he developed the whole concept of the heterodyne receiver, but could not come up with a successful oscillator to make that receiver function. So Fessenden, for his experiments, built this 420-foot mast in Plymouth, Mass, very close to where the Pilgrims landed. And there's a photograph of his tower. And his other station was in southwest Scotland. So this is the heterodyne receiver that was patented in 1901, but totally unavailable, unable to make this work because there were no vacuum tubes. Nobody knew how to build an oscillator, and the whole thing kind of sat on the table. So US patent 706740 turned out not to be practical. But then the Audion 3-electrode triode came along in 1906. DeForest was the guy who invented it. He called it the Audion. But DeForest was kind of an interesting character too. He developed this thing called the Audion, but he didn't have any real clue as to how it worked or why it worked. So he wasn't able to make anything practical out of it that related to radio. And here's a photograph of that first Audion vacuum tube. And if anyone has ever seen what schematic diagrams of a triode look like way back, it was a jagged line, and you can see in this photograph that it was a literal representation of what the grid looked like. Kind of looked like a paper clip that was kind of bent into a zigzag shape. So this looks a whole lot different than a vacuum tube that came later, but it was the very beginning, 1906. So no radio practical technology came out of this yet. So the next thing that comes along is Marconi has now figured out that in order to make a business of communicating across the Atlantic, you needed very big antennas. So he gave up on the Table Rock location and built this huge antenna system, one in Glace Bay, Nova Scotia on the right side. You can see the power plant there. He had to generate his own AC power. There was no AC power available locally. And on the left side is the other transmitting station in Ireland, a place called Clifton, on the west coast of Ireland, west of Galway. And this is a photograph of the antenna. It was 200 feet high, 200 feet wide, and 1,000 feet long. There was a fire at this station in Glace Bay on the right in 1909, and by then they had figured out that the antennas in this photograph were not big enough to be reliable. They were better, but weren't big enough. So they took advantage of the fire, which disrupted their commercial operations, and they rebuilt these antennas to be much bigger. Here's a look at the technology that Marconi used. It was a 300 kilowatt rotary spark transmitter. Estimated ERP in Clifton in 1907 was 20 kilowatts, and that was at 54 kilohertz transmitting frequency. And in Glace Bay, Nova Scotia, about 38 kilohertz, the estimated frequency. So this is a photograph of the condenser. So the technology they used to develop high power was to store energy in this huge condenser. We call them capacitors now, but back then they were condensers, so I didn't change the terminology. Estimated to be 1.8 microfarads at 18 kilovolts. So this condenser would store that energy, and then the spark transmitter, when it transmitted, would deplete that energy. And then when you let up on the key, the capacitor would charge again, and then the spark would go out with the next Morse symbol. So this capacitor was 350 feet long by 75 feet wide, 1,820 metal plates, each 30 by 12 feet. This is what you call a big capacitor. Quite incredible technology. And this is a map of what the upgraded site in Clifton looked like after the 1909 fire in Glace Bay. This antenna was 2,500 feet long, 800 feet wide, and 400 feet high. And when the system went operational again in 1910, it was much more reliable. And they were now starting to take business away in a serious way from the transatlantic cable companies. Well, in Ireland, it was so rural there that not only did they not have electricity, they didn't even have a ready source near this town in order to generate electricity. So, of course, if you're in Ireland, what do you use for a source of energy? You mine peat. No coal available in Ireland, but there's lots of peat. If anybody's ever been to a pub in Ireland, they're heated by peat in the winter. So Marconi built his own peat mine. He built his own railroad to carry the peat from the peat mine to the power station here. And so this was a very self-sufficient operation. So Captain Armstrong here, that rank in World War I, was the inventor of the first receiver that we would recognize as a receiver. It was a regenerative receiver that used that Odeon tube that was invented in 1906. And this was a receiver that was capable of receiving CW signals for the first time. So now, although the high-frequency alternators, electromechanical alternators, capable of generating very pure CW signals in the VLF frequency range had been around for well over 10 years. There was no receiver, but Armstrong developed that receiver. So and this is what the patent looked like, 1913, a single Audion. And the sensitivity of this was dramatically better than those very crude coherers that I showed you earlier. The improvement in sensitivity was just enormous. So this signaled the onset of electronics in the technology of radio communication. And believe it or not, a lot of hams think that single sideband was developed after World War II, but that's absolutely not true. The first patent for a single sideband transmitter was awarded in 1915. Well, it was submitted in 1915, December 1st, 1915, awarded after World War I in 1923. So the technology of single sideband goes back a very long way, and it was developed shortly after Armstrong's original regenerative receiver patent. So now we'll shift over to the Navy because that's where the technology really started to develop rapidly. Stanford Hooper was a rear admiral who was generally considered to be the father of U.S. naval radio. And this is a photograph of the three towers that were located at the U.S. Navy's first big radio station in Arlington. It was built in 1913, was torn down right at the beginning of World War II so that the commercial airport in Virginia could be opened, and these towers were too much of a hazard for what's now called the National Airport. So the towers were taken down so the airport could be prepared for operation. These were this was two 450-foot towers and one 600-foot tower. That building in this photograph is still there. It's used as a naval support, small naval support operation. It's called Buildings 1 and 2 at the Courthouse Road in Arlington. This was 10 kilowatts, operating at 113 kilohertz, and it's only on only 13 acres of land, just behind Arlington Cemetery. And a pretty good chance this photograph was probably taken from Arlington Cemetery. This is a photograph of a 100 kilowatt synchronous spark transmitter that was installed in that radio station when it opened. The synchronous spark is the device on the left. The spark, you can see the spark gaps on that inside that black enclosure on the left side. So World War I came along, and by then Marconi was in the process of developing a worldwide transoceanic communication system. So he had built this transmitting facility in New Brunswick, New Jersey, and this is a photograph of the building. And when the U.S. entered World War I, the Navy seized all radio stations in the United States, including this Marconi station. And this Marconi station became one of the primary means for the U.S. military to communicate with its forces in Europe during the war. Well, Marconi's transmitter technology was still rather crude compared to the high-frequency alternators developed by Alexanderson, and the Navy decided that in order to reliably communicate transatlantic for wartime use, they needed to replace Marconi's already very obsolete transmitters with these 200 kilowatt Alexanderson alternators. And here's a photograph of those alternators. They weighed 100 tons. And this is still electromechanical technology. There's nothing in here that one could call electronics. This was electrical technology developed in the 19th century, extended to be able to operate at 22 kilohertz. And this is the antenna. We're in an age of radio that is sometimes referred to kind of tongue-in-cheek as Jurassic radio, because everything is so huge. And this was the antenna that was installed in New Brunswick, New Jersey to operate with this station. 5,000 feet long, 600 feet wide, and 400 feet high. Good thing we didn't need this in multi stations today. There wouldn't be any. And the estimated ERP of this entire facility was 10 kilowatts. So this fellow's a ham, 1AJ was his call sign before World War I. And he was a member of a wealthy family that had an estate in Bar Harbor, Maine. And he had quite a capable amateur station back then. And he noticed, he was still a civilian, he was listening to the naval communications between the big station in New Brunswick, New Jersey, and Europe, and then he could see that the Navy's receivers in the U.S., and the Navy tried putting their receivers, first of all, in Washington, D.C. Well, that didn't work because of all the electrical interference. Then they tried to move to the coast of New Jersey, and that was a little better. Then they tried Cape Cod, that was a little better. And then this ham, 1AJ, was able to copy the communication from Europe perfectly. And he could tell that the Navy was struggling, and the messages were getting repeated over and over. And he contacted the Navy and told them that up here in Maine, we can copy these messages perfectly, or I can copy them perfectly. And the Navy sent a couple of engineers up there, and this ham station could copy the communications from Europe absolutely error-free. So for Brie, and this was early in the war, the first couple of months of the war, offered to the Navy, said, if you give me a commission as a naval officer, I will complete the building of the station for you and command the station and operate it for you. And the Navy had a very hard time getting to yes. So they continued to struggle with their stations further south in the US, but eventually, as you can see in the photograph, they took him up on his offer, and Fabry built this station for the Navy, and he was the commander. Interesting ham radio story. And this is a photograph of the station right around the end of World War I, when the Navy had developed it even further. The antenna you see in the photograph, if you look at the red arrow, there were a couple of support structures. The one on the right side is a little bit easier to see. This is a multi-turn VLF loop receiving antenna. Very similar to the magnetic loops that hams use today for both transmitting and receiving. It's a simple loop antenna. It was the most effective antenna they found. There was a lot of antenna experimentation that was going on at this site and other sites during World War I, because communication was vitally important. And this was the best technology that they had available. So W3WV was a well-known member of the Potomac Valley Radio Club. But PVRC didn't start until 1947. So this photograph of Leo was taken shortly after World War I, when he was one of the leading technologists in the development of radio in the US Navy. And this is one of the many receivers that Leo was involved in developing. And this receiver was the first mass production standard Navy receiver. The Navy observed that they could buy commercial receivers, but they wound up all being different from one another. And you really can't operate a large-scale military operation when all the equipment is different. You can't support it. So the Navy engaged RCA and other companies to build these receivers that the Navy had developed, and thousands of these were built. And some of them are still sold every so often, but not many of them survived. Well, why was radio so important? At the onset of World War I, it would have been 1914 when Germany and England got at it. The very first day of the war, British submarines cut all of the German cables, subsea cables. They were all cut. So, it didn't take a lot of imagination for the US Navy to realize that if the Germans lost all of their subsea telegraph cables, that when the United States got into the war, if we ever did, they didn't know if we would, but if we ever did, that the Germans would probably do the same thing. And this is an image of a submarine that was outfitted by the Germans with the technology that allowed them to cut cables. Well, as it so happened, so this was the reason why the Navy put this tremendous focus on developing radio technology for transatlantic communication. It was an extreme important enterprise during the war. Well, as it so happened, this submarine did in fact attack some of our cables, but they found the wrong ones. They didn't manage to cut the transatlantic cables, but they cut a couple of relatively unimportant cables connecting the east coast of the United States down to the Caribbean. And they were repaired just 6 weeks later, and the Germans never did get a chance to cut any of the transatlantic cables before the war was over. So this submarine was the driving force for the very rapid advancement of radio technology during World War I. This was the headquarters of Naval Radio, Naval Communication Service during the war and shortly after the war. You can see some antennas on the roof of this building, and this is where they tried to receive those signals from Europe, right in the middle of Washington, D.C. That was not going to work. That was one of the receiver sites, and it worked fine, I'm sure, with strong signals in the U.S., but for the weak signals from across the Atlantic, this just didn't work. So, of course, no one knew how long this war was going to go on, and no one knew when the Germans were going to be able to successfully cut the transatlantic cables. So there was a crash effort to build 2 huge radio transmitting sites in the United States. The first one that got underway was NSS in Annapolis. And the very first slide where I showed all of those antennas was NSS right at the end of its operation. So this was the first NSS station. It was 4 600-foot towers. The Navy still hadn't learned the lessons Marconi had learned 10 years before. You know, Marconi made the mistake of starting small and gradually getting bigger and bigger until he got to the point of these 5,000-foot long antennas. Well, the Navy went through the same learning curve again 10 years later. They built the antenna systems too small. So this little 800-foot by 800-foot antenna was not reliable enough for transatlantic communication. But the Navy had another plan. They had developed a plan to build a much bigger station in North Carolina, and steel was in short supply during World War I. So their plan was to build 400-foot towers made as if they were chimneys, brick chimneys. So the towers were going to be brick rather than steel. But the war was over before that station was built, so it never was built. So we never got a chance to see a huge radio station supported by 400-foot brick towers. So another figure in radio development was Paulson. He invented the transmitter that was favored by the Navy, the so-called ARRL transmitter. And ARRL technology is quite a bit different than SPARC. A lot of hams, when they hear that term, they assume that's just a pseudonym for SPARC, but it's not at all. ARRL is a continuous arc in a hydrogen environment. Yeah, hydrogen, very explosive. So it was sealed. But it was a continuous arc, whereas a spark, once you ignite it, will not sustain itself for very long. And these were the transmitters, the Paulson ARRL transmitters that were installed at NSS in 1918. These are 500 kilowatt transmitters, a pair of them, and to give you an idea as to how big they are, you can see that photograph of the transmitter operator there. So these things, I don't know what they weighed, but they were probably 100 tons again. So this is still the state of the art. Electric arc and a hydrogen gas, which converts high power DC into a RF alternating current. But it's not in the modern terminology we would use today, this creates a almost a CW tone, but the phase noise is incredibly bad. It will probably be maybe 10 dB down from the signal of interest. So an oscillator with extraordinarily bad phase noise. Whereas the Alexanderson alternator that the Navy used at the New Brunswick site, again, I don't know what the phase noise was on that, but I've heard there's still one of these Alexanderson alternators in I think it's Sweden. And they put it on the air every year, and I've heard recordings of the signal, and it sounds just like the CW that comes from a modern K3. It's absolutely perfect. And I've heard recordings of the signals from these electric arcs, and they sound a little bit better than the spark transmitters, but not much. So during World War I, Armstrong started working on the next advancement in the technology of radio receivers. And by then, vacuum tubes were around. They knew how to develop oscillators. And you remember this so-called heterodyne receiver that was patented 10 years before this, but couldn't be built because there was no oscillator that you could buy or build. Well, Armstrong solved that problem, and the superhet receiver very quickly obsoleted the regenerative receivers that by 1919 were kind of the standard. So this was patented, the patent was filed in 1919, but he did his work during World War I when he was in the Army, and was patented in 1920. And this is a photograph of the standard regenerative receiver that the Navy had developed in 1920. Thousands of these were made, and occasionally you see these for sale for big bucks. And these were manufactured by the Navy for about 10 years. So now the technology is starting to shift. World War I is over. The hams finally get permission to get back on the air after a fight with the Navy. And the hams got back on the air late 1919, early 1920. They were starting to be able to communicate over fairly long distances, and by 1921, there were actually some successful communications across the length of the US, but not very reliable. That's where the name American Radio Relay League comes in. The relay was necessary to reliably communicate coast to coast, but there was some direct coast-to-coast communication before this test took place. So radio amateurs led the revolutionary shift to high frequencies. At this time, generally the frequencies above about what we would call 1500 kilohertz were considered to be junk. That's 300 meters and below. So the hams had pretty much unrestricted access above 1500 kilohertz. And that's the technology that hams were starting to use to communicate across the US. So they tried to interest the hams in Europe to participate in some tests of transatlantic communication, but the hams in Europe just couldn't get their act together. So after some failed attempts, the American Radio Relay League sponsored a de-expedition to the UK, but one-way tests only, so only receivers were sent. They did not attempt to get a transmitting license. And this is a photograph of the tent, and both a super regenerative receiver on the left side and a super heterodyne receiver on the right side that were installed in this test in Scotland. Here's a photograph of the super het receiver. It was a 9-tube receiver. And at that time, the standard way of building receivers was to build the RF tuners in a separate enclosure. So although this is one receiver, the RF circuits are on the left, connected over into what they called a detector at the time on the right. So the hams had to build a transmitter, and of course by then the relatively low power vacuum tubes that we use for receivers were developed into high power tubes by RCA primarily, but other manufacturers too. And this is a photograph of their 250-watt tube, the UV204. And several of the hams who worked for RCA decided that this transatlantic test in 1921 was going to be a success. And they set out to use the best technology available to them from their work at RCA to build a station that they felt was absolutely certain to be able to be heard in Scotland. So this is a photograph of the transmitter they built. Call sign was 1BCG. That was the call sign of one of the members of the group of hams who built this. It was 4 of these 250-watt tubes, one as an oscillator, 2 as an amplifier. The 1921 transatlantic tests were a big success, but the Navy was still plugging away at VLF. And this is a photograph of NSS in Annapolis at its next stage of development, where they're starting to learn the lessons from Marconi of 15 years ago, and they extended their antenna to be 2,500 feet long. So you can see the 4 original towers there in the center of the photographs, and then they added some more towers further down the peninsula to the right. So now they're up to 50 kilowatts ERP. Much better, but still not enough to be completely reliable for transatlantic communication, 1922. Well, I mentioned W3WV, who later became a PVRC member. When he was working for the Navy at the Naval Research Laboratory, he built this 10 kilowatt crystal control transmitter. So this was a new crystal control was a new technology. Here's a photograph of the transmitter he built. And it was installed at NSS Annapolis in 1925. So this is actually, the one that was installed at NSS was a duplicate that was built for the Army, and it was installed at the Naval Station. And of course, what they discovered, just like we did, is that with, you didn't need 10 kilowatts. On HF, they could reliably communicate it over enormous distances with a lot less noise than at VLF. So the whole focus of the NSS station started to shift from VLF to HF. And the focus of naval communications also started a major shift. And here's a photograph of one of the HF receivers that was designed by future PVRC member W3WV. This particular receiver was installed on a blimp, the USS Shenandoah. And the Shenandoah met a tragic accident. Everyone on board was killed. This receiver was recovered from the Shenandoah. So you can see it's labeled experimental HF receiver, 2,000 kilocycles back in those days to 17.2, I'll call it megahertz. So this is technology 1924. Things are moving rapidly now that HF is, the hams proved it would work. The Navy, by the way, worked in very close cooperation with the ARRL during that period from 1921 to the middle 1920s to develop and prove the utility of HF communication. If you look through QST magazines, which you can easily do now on the ARRL website, if you're an ARRL member, you can read some of the articles about the cooperation between the hams and the US Navy during this period. So 1931, HF communication is now getting very much into the commercial world. AT&T, an engineer called Edmund Bruce, patented this antenna in 1931 called a rhombic. And compared to these, remember the term Jurassic radio, compared to the Jurassic radio antennas that were a mile long, this was a miniature antenna. Most of these antennas only at 500 feet or 1,000 feet long, or maybe even less. So this was filed in 1931. The patent wasn't awarded for about 10 years later. but this became the standard antenna for military and commercial long-haul HF communication, all during the 1930s, and they were still widely in use until the advent of satellite communications in the 1960s. Here's a photograph of a VLF transmitter that replaced the ARC transmitters. This was 1932, 300 kilowatt VLF transmitter at NSS. 50 water-cooled 10 kilowatt vacuum tubes. And the HF transmitters, this is the 50 kilowatt standard Navy HF transmitter, 50 kW water-cooled. And it was widely used at shore stations and at NSS Annapolis. Well over 100 kilowatts ERP with this transmitter and rhombic antennas. And this transmitter was relatively small compared to some of the other transmitters used by the Navy. It was only 8 feet tall, 20 feet wide, and weighed 1,600 pounds. So technology is improving on its way to things like the K3. And this was the state of the art of receiver technology in the 1930s. This was the Navy's superheterodyne band switch receiver built for the Navy by RCA. It was the Navy's first 115 volt AC powered HF receiver. And there was also a VLF version as well. Occasionally these receivers show up for sale also. They are huge. It wouldn't fit on your desk. And this is a photograph of that main Navy site in downtown Washington, D.C. at the main Navy building in Washington. And you can see the receivers on the operating tables. What you see on the table there is a mill. It's a typewriter that types only in capital letters in front of a rows of these RAA and RAB receivers. So an interesting thing happens in the 1930s. You may remember that Ham 1AJ who built that naval receiving station in Maine. Well, after World War I, that naval receiving station wasn't well maintained, and it was in kind of dilapidated condition. And at the same time, Rockefeller decided he wanted to build a park on the coast of Maine, and his intent was to donate that park to the United States to become a national park. But in order to meet his dream of building this park, right in the middle of this park was this terrible, dilapidated old naval radio receiver station, and he needed it to be gone. So Rockefeller volunteered to the Navy that he would build for the Navy another receiving site right on the ocean, about 20 miles to the north. He would build the entire station, make it ready for the Navy's use, and the Navy could shut down this old dilapidated station that was built in World War I. And the Navy had a very hard time getting to yes. But eventually they did. And this building that you see here is now part of a national park. On the coast of Maine, you can visit it. It was not built like any other Navy facility I've ever been to. Rockefeller built it the way he wanted it to, so it's quite decorative. So it was opened in 1935, and the Navy old receiver site used in World War I was shut down. So this is a look at the state of the art of NSS as the U.S. was preparing to go into World War II. And you'll see by 1938, the Navy had finally learned the lessons that Marconi had learned by 1910. So it took the Navy almost 30 years to figure out that for VLF transatlantic communication, you needed a 5,000-foot long antenna, and they made this one 800 feet high. And this was the state of the art as we went into World War II. 130 kilowatts ERP at VLF, and that was enough power to be able to communicate with submerged submarines. And this is a photograph of a rhombic antenna farm that AT&T built in 1938. It was the first large HF receiver site specifically built for rhombic antennas. And I don't know how many rhombic antennas are in this map, but there must be a couple of dozen of them at all different bearings. And this is what HF receiver sites looked like, all during the 40s, 50s, and early 60s before satellites came along. A typical HF military or commercial receiver site was about 1 square mile, and it was full of rhombic antennas and open wire feed lines. It was quite a sight to see. Well, Morse was the standard way of communicating, but that was kind of unsatisfactory. It didn't scale very well to the massive amount of communications needed to support naval operations as we were about to enter a war. So the Model 15 teletype was built so the Navy could transition to long-haul frequency shift keyed radio, and 200,000 of these Model 15 teletypes were built for the Navy over a 30-year period. And here's a photograph of the Naval radio receiver station that was built as the receive site for NSS. Typical for radio communication in that era is that a transmit station was built and the receive site was built at least 20 or 30 miles away. And this receiver site was fairly close to Washington, D.C., about 10 miles away. And there's a photograph here of Model 15 teletype on the left-hand side there, and there's another one on the right with some RCA receivers and on the left, and some of the RBC HF transmitters built in the 1930s on the right. And this station continued in operation until the late 1960s. So here's a photograph of the next generation VLF, LF, and MF receiver. It was a tuned radio frequency receiver. And without getting into a lot of detail as to how the technology worked, the idea of a tuned radio frequency receiver is that there was no frequency conversion whatsoever. And this was very, very important to the Navy, because if you had an oscillator on a Navy ship, if by any accident that oscillator radiated through either through power line connections or the antennas on the Navy ship, that Navy ship could be located and sunk. So the Navy did not allow VLF receivers of the superhet design with local oscillators on Navy ships until well after World War II. So this TRF receiver was developed that did not require oscillators. All of the detection circuits were at the same frequency as the radio signal being received. By the way, for anyone interested in exploring these technologies in more detail, you can look through these slides, and Google is your friend, and you can learn a lot more about any of these topics using Google to help you. So this is the this was the MF and HF receiver that were manufactured by RCA, and another PVRC member, Don McClendon, W3EIS, who later became very well known as a contester as W3IN and later N4IN, was the design engineer for this receiver. And many, many thousands of these were built for the U.S. Navy. I don't know exactly, well, there it is, 80 pounds is what this receiver weighed, far from a K3. So in order to improve the reliability of HF communication, by this point, the HF radio communication was really vital to the operation of some critical naval circuits. And diversity receivers were developed. And this is on the left is a photograph of the 3 receivers that were used in the triple diversity system. And on the right is a more close-up photograph of the controls on just one of those receivers. An enormous number of controls. I can't imagine what it would take if you had to QSY to another frequency. Well, actually, I do know, because all these knobs are calibrated. So if you had to, when the time came to a QSY to a different HF frequency, it probably took 30 minutes to QSY this receiver to a new frequency. This triple diversity receiver was 4 racks and weighed 1,700 pounds. So I guess we hadn't yet fully escaped Jurassic radio by World War II. And this receiver was called the RCP, Triple Diversity Receiver. Not very many of these were built. This was the Navy's first SSB and ISB, independent sideband HF receiver, built by Bell Laboratories for the Navy, called the REA. So independent sideband is like having two single sideband transmitters, one operating lower sideband and the other operating on upper sideband, and all feeding the same transmitter. Hams, there's no reason to use ISB for hams. In fact, we wouldn't be allowed to use it. It takes too much bandwidth, but widely used military and commercial during the 40s, 50s, and 60s. This is the Navy's first single sideband exciter, 2 kilowatts, built in 1943. And another transmitter manufacturer was a company called Press Wireless. They built these transmitters for the press circuits, newspaper circuits that ran Trans-Pacific and Transoceanic. And because Press Wireless had developed these transmitters for their own use, they were pressed into operation by the Navy to build transmitters for the Navy. And this was the TEB transmitter. This is a 15 kilowatt transmitter used at 400 words per minute radio teletype. So this transmitter is an extension. So they took that transmitter, the 15 kilowatt transmitter, and put a power amplifier on it, and it ran 40 kilowatts. And this is the PW40, 40 kilowatt HF and FSK and CW HF transmitter. So some of you may be aware that the United States built a two-way secure radio communication circuit between Washington and London. And that was used by President Roosevelt regularly for secure communications, encrypted communications, so he could communicate with his counterpart in England. And this is a photograph of the 30 kilowatt transmitter that was used for Roosevelt's transatlantic telephone circuit. Well, the end of HF radio is in sight. This article appeared in Wireless World magazine right at the end of World War II. And it's conceptual. There wasn't enough information in this article by Arthur Clarke to tell you how to build, how to go about putting up communication satellites. But all the concepts about how to go about doing that were here in this 1945 article. And this was the beginning of the end of military use of HF communications. But that would take a while. The heyday of military HF communications ran right through the early 60s. So technology continued to advance. The next generation of Navy HF transmitters was in 1948. Still pretty massive stuff. These were built by Collins, but these were now capable of more rapid QSYing. And here's a photograph of the LF transmitter that was used at NSS. So this was at a 50 to 150 kilohertz. So this was not used for submarine communication, but it was used for fleet broadcast. And this is still a pretty large transmitter. And they installed an 800-foot tower, quarter wave vertical, to operate with this 50 kilowatt transmitter in 1952. So one of the technologies developed in the 50s was called voice frequency telegraphy that allowed multiple telegraph channels to be communicated over a single sideband. And this was a 12-channel radio teletype system that could be carried on a single sideband transmitter. And a pair of these could operate on an independent sideband transmitter. So what about Navy ships? Very difficult to put up a 1 square mile antenna field on a Navy ship. So they needed the technology to be able to share one antenna among multiple transmitters. And this multiplexer The ANFRA49 was developed so that three HF transmitters could share a single antenna. But there was a restriction that the frequencies of those three transmitters had to be separated by at least 10%, and these were installed on some Navy ships. So a big revolutionary change in antennas came about in 1957. Two engineers at the University of Illinois developed the log periodic antenna, and countless thousands of these very large antennas were built, and many are still in use today. But the real heyday of these antennas was in the 1960s and perhaps through the early 70s. And I think a lot of you have probably seen these antennas. A typical antenna like this Collins 237B was, the rotator was on the ground, the mast ran up through the tower. That boom on the antenna was probably about 50 feet long, and the longest element is probably about 70 or 80 feet. Thousands of these were built. There are probably 100 in existence today. And this is the wideband transmitting antenna for omnidirectional use. So for the Navy's point-to-point communication, they would typically use the log periodics. They were broadband, so you could feed many transmitters into them. And for their broadcasts, where they wanted to transmit from one point to many receivers, they needed omnidirectional antennas. And the conical monopole vertical antenna was patented in 1963. And again, thousands of these were built in the heyday of HF radio during the 1960s. Not very many of these survived. And transmitter technology leaped forward. Some engineers formed a company called Technical Material Corporation in the 1950s, and they were successful in winning some of these Navy contracts, and they manufactured quite a few of these 10 and 40 kilowatt transmitters for the Navy during the 60s. These were capable of single sideband, independent sideband, CW, and FSK. And here's their diversity receiver, still pretty big. This is dual diversity, but capable of rapid QSY, unlike that receiver with a zillion knobs on it that took about a half hour to QSY. And this is kind of the maximum state of advancement of the state-of-the-art of high-power HF transmitters in the Navy. This was three transmitters, 10 and 40 kilowatts, depending on the use. The ANFRT 83 and 84, they were manufactured by Continental Electronics, and they're still very much in business. And RF Communications, which is now, the lower power transmitters were made by RF Communications, that's now part of Harris Corporation, and the 40 kilowatt transmitter was built by Continental Electronics. And more than 370 of these were built. Okay, so the first satellite communication system was operational before the launch of the first satellite. How could that be? Well, last I knew, the moon was a satellite, but it's a natural satellite. So the Navy needed to have a form of communication that was more reliable than HF under extreme disturbances. Anybody who's ever operated HF knows that things happen in the ionosphere that sometimes make it impossible to communicate. So the first military satellite communication system was operational before there were any satellites other than the moon. And this is a photograph of a famous ship, the USS Liberty. Some of you may recognize that that was the ship that was attacked by the Israeli Air Force in the Mediterranean. And there's a photograph of the communication moon relay terminal. So this is a pretty good clue that HF radio is doomed. And this was the Navy VLF station in Maine that's still very much in operation. And you can see the drawing of the two redundant antenna systems there. So either one of these huge antenna systems can operate independently or they can operate together. Um, there are 26 towers in this at this VLF station. Two 1,000-foot towers in the center of each of these two arrays, and then the two arrays are surrounded by 12 towers up to 875 feet tall. And this station has an ERP of 2 megawatts at 20 kilohertz. Quite an advancement from the early Marconi days, but still kind of the same technology. These two antennas are 6,100 feet in diameter. There's a pair of them. So that's why the Annapolis station ultimately became obsolete, because this little tiny antenna that was a mere 6,000 feet long was no competition for a pair of 6,100-foot diameter redundant antenna systems up in Maine. So ultimately, when the Cold War came to an end, the station was disestablished. And the last communications to be turned off here was the VLF broadcast. The HF transmitters were shut down several years before 1969, and then all these towers and antennas were removed in 1969. But we put up our little NSS antennas on Armed Forces Day on the same facility once a year, and hopefully we can do it next year. So this was the state of the art of naval receiving antennas back in the 1960s and 70s. This is a pair of fully steerable 450-foot diameter receiving antennas for diversity use. That's why there's a pair. And this was built in the mountains of West Virginia, and that naval base was often referred to as the West Virginia Navy. So just briefly, this kind of ends the HF-related part of this presentation, but we'll go through a little bit of what happened afterwards. This was the Navy's first communication satellite system. They used 25 kilohertz bandwidth UHF channels that were leased on a maritime satellite communication satellite. So this was not a dedicated Navy satellite, but 600 Navy ships were equipped to use the Marisat satellites in 1976. And here's the end of NSS. The tower was demolished in 1999. I didn't see this in person, but I've seen the video, and this is just a little video capture of the video. 3 of the towers from NSS remain, but unfortunately for our Armed Forces Day activities, we don't dare use these towers. And why would that be? They're directly in line with the firing range for the U.S. Naval Academy. And although this area is open for use, the Navy closes it whenever they wish. So if they ever decided to operate the firing range, and they might do that with only a day's notice, this whole area is closed off and our NSS operations would be terminated. So we decided not to use these towers, because without notice, we could be shut down. And we definitely wouldn't want to be at the end of a firing range. So this is what the NSS operations look like at Armed Forces Day. We sure would have enjoyed doing that this year, but everybody knows why that didn't happen. So this is the modern new NSS with a couple of 48-foot AB 577 military masts, a couple of tents, and half a dozen K3 transceivers. And this station was far more capable than the early naval stations of, let's say, 1920 and before. And here's a photograph of some of our operations during Armed Forces Day from the NSS grounds. And we were visited during one of our operations by the Director of Naval Intelligence. And Admiral Teig had been a licensed ham for a few years when she was in high school, but no longer licensed. But she made a SSB QSO during Armed Forces Day with us. And here's another photograph of the original NSS station Uh, and this was our result from in 2018, 400 QSOs during Armed Forces Day. So we thought we did really well, but there was another member of PVRC who became a Navy admiral, three-star admiral. It's called K0DQ, Scott Redd. And here he is when he was a cadet at the U.S. Naval Academy. He was operating Armed Forces Day in 1965. So how did they do? Well, they did so well. The idea was to beat the Army Armed Forces Day, WAR operation. They made 2,894 contacts. Remember how many we made? 400? Actually, 900. 400 on CW, almost 500 on phone. We made 900. And Scott Redd, back when he was a cadet at the Naval Academy, and he and his crew made almost 3,000 contacts and received this letter from the Director of Naval Communications congratulating them. So is anyone surprised that this midshipman became an admiral? Not based on these results.
He was actually at Visalia one year, many years ago.
He's quite a guy.
He is a great guy.
Yep. And a very accomplished contester. So here's the crew of operators at NSS Armed Forces Day. And here's the final slide. If you want a job at NSS, this guy was applying. He wanted a job sending V's. I don't know if he got the job. And that's it. So I hope you enjoyed it. And anybody who wants to know more detail, as much detail as you could stand, you could find by